So let me do the following because we have a similar problem in your homework. So we're looking for this Jacobian, right? And the definition is right here. You take the derivative with respect to xn of whatever this guy is, and the derivative with respect to bn, whatever this guy is. You do the same one for the bn plus 1, and there you go. So if we look at the Euler method, this is the answer that you get. 1 and 1 right here, and then you get this delta t up here, and delta t down here. And then what I did is that I said, what is the acceleration for the harmonic oscillator, and stuck it in there so that we could get the eigenvalues of this and talk about that. So this is the same for the Kromer algorithm. So here we take the derivative with respect to xn plus 1. No, the derivative with respect to xn. Oh, the xn plus 1, right? So if we look at it, this is xn bn plus 1 delta t. This bn plus 1 is something that we found already in the Kromer. The difference between this one here and the Euler is that this is the bn plus 1 instead of the bn. So once we stick that in here, we get this quantity, and then we can take the derivative with respect to xn. So derivative with respect to xn, we get the 1 plus, and you see that this guy, the bn depends on xn. No, right? So this guy times this guy is 0, the derivative of that, and then this one times this one gives you the delta t squared. And then you have to figure out what is an when you take the derivative with respect to xn. So that's where we're getting those values. And then we have to do the derivative with respect to bn, right? On xn plus 1. So you see, with bn, this is 0, this is 0, and this is the only guy that has a bn on it, and that's where you get the delta. So that's it, that's what you do there. So that's how you get those two values. Delta t is just this one, multiply with that guy. And that's what you would do. So then you look at the determinant of this and figure out what you need to do for the homework. The homework, let me close this. Homework is available. I'm not giving any extra time for this one because if not, I'll be behind on everything grading wise. It's due Tuesday at midnight. So make sure you start it right now. And the first exercise is show, this is from symplectic algorithm. So you see how this assignment is behind because this is from week 1 and we're in week 4, right? So I cannot give extensions on homework because of that. Otherwise, we're only going to get 3 assignments throughout the whole semester. And that wouldn't be fair, right? You want to have as many assignments as possible so you can improve your grade. So the first part is show that the Euler algorithm does not conserve angular momentum. I think I did this in class for the Kromer, right? You can do this analytical ways to do it. So that's what I did in class where I showed you where this angular momentum is the r vector crossed with the velocity vector, right? So at every time step, is it being conserved? Or did it change? And that's what you're doing here for the Euler algorithm. And then the velocity algorithm is area or phase space preserving, while the Range-Kura is not. So for this question, both questions, you could do this calculation numerically. You can do a calculation and say, like, am I doing this? Let's see, I could show in some problems that the angular momentum is not conserved with the Euler algorithms, like plotting it after I do a simulation, right? In a system that is angular momentum conserving. What's an angular conserving system? Angular momentum conserving system. A central potential, right? So you put your planet orbiting the sun. Simulation, you can plot the angular momentum. You can do this, or you can do the analytic approach, which is writing it up, right? And then do the calculation, not calculation, but, well, not numerical calculation, but rather that take this, substitute this, and do the algebra, right? For this one, again, you can do it two different ways. The analytical way, how would you show that something is area preserving? What's the analytical way of doing this? Sorry? You're looking at the determinant, right? Because what are you doing when you do the determinant is that basically you're taking a cross product of two vectors. So you have a vector going this way and another one going that way, right? You're getting the cross product as the area. Make sense? Of the two vectors. That's what your cross product is doing. And numerically, anybody knows how you would do it numerically? If you had to do it with a calculation, what would you do? Well, you would take a piece of phase space, right? So basically, you do calculations of maybe is you go from dx to dx plus delta, and then this is maybe dp plus sigma or something, right? And you take a bunch of points from here and see how they evolve in time. You take all of those points and you see where they end up in time. Can you see that in the board? Yeah. All right, well, you have to get out because you're so close. But the idea is that is this thing area preserving? Did that? This is where it gets hard, right? Because you will be thinking about discrete points, and now you have to show that those discrete points are going to occupy an area that is the same size area when they get evolved in time. Does that make sense, though? So that's a numerical approach to doing it. So you can do it analytically. Maybe you don't like programming, so you don't want to do that. But you really like working with algebra and derivatives and things like that. And that would be showing that the area is preserved. Maybe the shape is not. In fact, that's what I was telling you guys, that when we look at the shape can change, but the area has to stay the same.
Excuse me. So we should have, evaluate the evaluation of this area in the time and show that it is constant.
Yep. And that all these points inside of this square, when you plot them at a different time, are occupying a section of area that maybe is the same. Now, it might be really challenging. I don't know. It depends on how you think about things. But that's the numerical approach. So there's no reason for you to just do it analytically or just maybe you find a different way to do the homework. All right. Then exercise 2 is very similar to the previous homework. So you did the previous homework. You know how to do this part, setting it up. But now you're looking at another Range-Kura. And the fourth order is in Playtech. So your code is changed by this, guys. Now you're doing this additional methods. And you're calculating this Laplace range and length vector, which I covered briefly in class. Those of you that took mechanics already have looked at it. I asked Dr. Babu, he's covering this maybe in the last 2 classes. For those of you that are taking mechanics this semester. Anybody taking mechanics? This semester? You are? You are? All right. So you've seen this in class, no? Not yet? All right, he's covering it then in the next couple of days. And then third exercise so that you get started doing with this kind of potential, doing molecular dynamics. And as the name of this part of the exercise says, They're more like billiards. All right. Questions about this?
Which one is more, could you show it again, like billiards?
It's exercise 3. All right, so start your homework early. This is coding. When you're coding, you think you're going to spend 15 minutes writing a function, right? But maybe it does take you 15 minutes to write a function. But then you have to multiply by an exponential factor the amount of time that you're going to take debugging. Right? Those of you that code, who says yes? Who says no? So I can hire you. I'll pay you double if you can code that well. So yeah, you might spend 15 minutes doing these positions and all of that, and 15 minutes putting these things because you did it before. So I'm breaking it down into pieces right here for you guys. You take maybe 15 minutes to do each part, but it's not trivial. And then if you make a mistake because of whatever reason, finding that mistake is going to take you an hour. So that's how coding goes. Questions? And no extensions because it's not fair to the rest of the class. And one thing that I've been noticing is people working together. I don't know if people work together in discussing how things are done. If you have questions about that, I don't mind. You cannot share codes, right? Or you cannot be like, oh, I already did it. Let me show you how I did it. It's discussing about how you do it. That's how you learn. If you already did a homework problem and somebody comes to you and tells you like, hey, Brian, can you help me with this one? And you already figure it out, you can't. Right? That's cheating, right? Does that make sense? And especially don't share the code. If you wrote a part of the code and you share it and it shows up in somebody else's homework, it's going to be bad for both of you. So don't share codes just like that. If you copied from some website, you found how to do the fourth order Ranjakuda from a website, and you have the code and you copy paste it from that, just acknowledge that part. Okay? I don't mind if to do that, but you have to keep acknowledging things. All right, anything else that I haven't talked about? All right, so let's get ready with the next part of the assignment here. So now we're in molecular dynamics. We've been talking about how to do them. We have, for instance, here, we have here a simulation of argon gas. And then we were talking last class about how you're going to have an equilibrium time. You put them in some positions, you're going to get, this is the kinetic energy over time. You're going to put an equilibrium time into the calculation because the system has to equilibrate. Maybe some parts of it had too much stored energy in them. Maybe some parts hadn't really reached the motion that you wanted because there were no particles to interact with. And after a little while, you get that the temperature is kind of like a good approximation to think of it as the average kinetic energy. Then if you want to cool down the system, you would rescale the velocity of each of the particles by a small, very tiny number. And then you have a gas, and you'll see that it cools into some solid. So another reason that this is interesting is that when you're doing the cooling down, when you're doing this type of cooling down of the system, you're going to reach, you're able to probe particles, how they solidify, right? How you make argon gas in this case. But actually you can change what you're doing in your simulation and find the absolute ground state of the system for a system that is not particles, but it's actually a system of equations. So that's how this method can be very useful, not just for that. Maybe you're looking for the minimum energy of a system in quantum mechanics, maybe, and this is a phase transition, right? You went from gas to liquid to solid. So you were looking for that kind of stuff in the classical molecular dynamics of the system. But if you build a system from interactions that could be mapping another mathematical problem, maybe you're finding the global minimum of a function. And that turns out to be very useful. Quantum mechanics uses this. So next on the agenda would be to talk about the Burial theorem. So we're talking about pressure in the system. How many of you are familiar with the Burial theorem? I've heard of it. Is burial. Yeah, what does it mean? Right. And the idea is as follows. Let's look at a container that has gas. So we have a container here. A container here is full of gas. And we're going to look at a small surface right here, ds. So let me pretend that I can draw, and this is a cross section of that surface right here. It's actually cooler than I thought it was going to come out. So we're looking at a small surface right here. Out of this thing, there's a normal vector coming out. So we have a container with gas. So we're looking at a small surface. This surface right here is ds. Like that, ds. And we can figure out what is the force, the pressure exerted on the wall. And that pressure is going to be the force on the wall. The differential force is equal to the negative of the pressure times this ds. Questions? Maybe you've seen this formula before, right? But this is what we're after, the pressure right here. So again, if you look at it, you can think of this as a section. If you were looking at a cross section of it, you would see that there's a normal vector, right? And which ways are particles feeling a force when they bounce off of that? Exactly opposite, right? All right, another quantity is that we can calculate this other quantity, G, which is going to be a sum over all the particles, position of the particles, and the force of the particle. In this case, this Fi is the total force on the eth particle. Ri is the usual position of the ith particle, and this is sum over all the particles. So if we wanted to calculate something like that, like this G, the quantity G, what we want to do then is do ensemble averaging, right? If we were doing thermal or statistical thermodynamics. In this case, with our molecular dynamics, we set up the system and we let it evolve over time so that the average of that G quantity is going to be given to us by 1 over tau, and then integral from 0 to tau of the time steps, and then the sum over I, Ri that depends on time, divided with Fi that also depends on time. Questions? So this force, right? I can rewrite it. And it's just the mass times the second derivative with respect to time of this Ri of time, right? I can do it like this. And what I know is that R dr dt is equal to the time derivative of R dr dt minus dr dt dotted with dr dt. So there's this calculus reference down here, right? Since we can do that, and you guys remember those kind of identities from calculus 2, right? Or is it calculus 3? All right. Since we can do that, we can rewrite an equation right here, this one right here, and have that our G is negative 1 over tau, the integral, tau right here, dt, summation over I, and then I have the m dr over dt squared plus 1 over tau R dr dt evaluated at tau minus R dr dt evaluated at 0. Tau is going to go to infinity, right? So what's 1 over tau? 0, right? So then that means that I can rewrite my G quantity as 1 over tau 0 to tau dt sum over I m dr dt squared. And this is equal to negative d n k b d, where d is the dimension, n is the number of particles, And then we have the Boltzmann constant and the temperature. If you're in 3 dimensions, this becomes 3. If you're in 2 dimensions, 2. If you're in 1 dimension, 1.
So
Yeah.
G is a random quantity we're considering, right? Like we don't have any specified definition.
No, it has a name. This has a name, the G.
Okay.
But you don't know it unless you took thermophysics.
Oh, yeah, I mean,
You heard that? So in thermophysics, they'll give you names. But yeah, it's not just a random thing. So let's recap. We have that the average Gibbs free energy is equal to the negative of the dimensionality and KB and the thermal. And another thing is that the force on I, on that particle I, is the sum over all the particles, the forces on all the particles where G cannot be I, plus the force on the walls. So the forces on I are the interaction with all of the other particles, except you cannot interact with yourself, that's not allowed. And if you're bouncing off the wall, maybe you're bouncing off the wall and that's why you have this extra term. Questions? No? All right. So let's calculate BL due to the walls. So in this case, we have the G due to the walls is equal to the sum, or the average sum over I, Ri, dotted with the force of the wall. And then this force is only at the surface, right? Because it's a wall surface. And what we have is that we will get the pressure of the system, summation over all the particles, Ri dotted with ds I. So we're taking elements dsi. So this is one of the little elements, ds, right? But there's so many, and this is the one, dsi, would be the one that is interacting with our particle I. That's the wall surface interacting with that particle. So this only happens at the surface. So actually this summation and averaging over the summation, I can actually replace it by saying that I'm going to do the integral over all of the surface of R ds. You guys are okay with that? All right. So now we do one of the theorems that you use in E&M, right? There's a theorem that takes you from a surface integral to a volume integral. You guys remember which one it is? Stokes, divergence. All right. So, and we do that, and we get negative P, the negative pressure, integral over the volume, and then the divergence of this guy, right? dV. Questions? At this point? So once you did all this, what am I gaining by putting it this way? So that means that the burial from the wall is going to give me negative pressure, and then an integral over the whole volume. This is in 3 dimensions, right? So here, there's 3 dimensions. That's why I'm taking this divergence. But it's actually the dimensionality of the system and the total volume. So we went from the surface to the integral so that we can say that this is just in 3 dimensions, it's going to be 3. And that's the dimensionality of the system. So in total, this quantity G average is the one from the particles interacting with each other, the one from the particles interacting with the wall. And we can rewrite this as the dimensionality N KBT is equal to this average IG minus this one from the volume. So now I can do some algebra and write the following. I take this P and this volume, put it on this side, and then that is equal to N KBT minus this guy, right? But there's a minus everywhere now. So I'm sending it to this side, so it's going to become minus, and minus becomes plus. This would be the only term that doesn't have a D on it, this one right here. So I add that over D, and that's the average over all the particles of Ri dotted with Fj. So this is particle I, force from other particles on it. At this point, you say like, wait, I've seen this before. Where have you seen this? Physics 1, right? Or chemistry 1 even. PB is equal to NKT. Maybe you know it as PBR and T.
Yeah.
With R being the exactly. But in this case, it's number of particles, Boltzmann constant, and temperature. What is that when it's just this term? That's the ideal gas. An ideal gas don't interact with each other, right? Here we have the ideal gas plus the term due to the interaction. So this is the first term. This first term is from ideal gas. Second term is interacting with each of the other particles. And that's the correction that you have to the ideal gas. Questions?
So what happens to the divergence of R? If that is equal to the dimension.
Yeah. So if this is in 3 dimensions, right? Del dot R is just going to be the 3 dimensions, the number 3.
Okay.
So it's the dimensionality of your system.
All right.
So now you know what the next term is when you see this in thermophysics. Maybe you have to calculate it sometimes, maybe not. All right, so this brings me to another topic that is of interest in molecular dynamics calculations. And it has different names. It's really important. Sometimes it's called the pair correlation. And other times it's called the radial density distribution. Yeah.
So in our previous equation, that's the energy conservation law, right?
Mhm.
Can we interpret the equation like that? This is our dq is equal to du plus dw. So the first term is giving us the internal energy. The PV is related to the Q, it, and this is actually our work done that is going like related to our kinetic energy. So it's just the thermodynamics first term, right?
Yes, yes. So that's what we're saying there, yeah. And
If we took the consideration we took our consideration of the fact that there is this interaction among molecules, and we also took care of the interaction with walls. And if we took care of the finiteness of the volume of the particles, so this equation should end up giving us Van der Waals equation, right?
yes. Yep. And you could add more terms, like for instance, maybe you're making those two particles collide with each other and make another molecule. Things like that, you would be adding more and more terms to this. But yeah, you're right. All right, so pair correlation or radial density distribution. When you're dealing with a many-body system, the correlations that you find is what defines it. So the question is, if a particle that is located at position R1 now maybe it should be for a particle located at R1, how many particles are at a distance R from it? So this is the question that we're asking, right? Let's first consider a system of just random particles. No, wait, let's do something easier. Let's do a uniform, non-interacting system. So I'm going to have my particle somewhere here. This is the one that I care about, right? And then it's just going to be completely filled with particles around it. Let's assume they're all the same size, right? So we could look at that there's uniformity like this. Then the next row goes like that. And so forth. And it goes in all directions, right? It's uniform everywhere. The same density, uniform density. So as we go a distance from the center, so I have my particle here, and then we start going a distance from the center, and there's another set of particles here, right? And then all of a sudden you feel that there's one particle or more particles or more particles. So I'm going to create a radius around it like this. in this uniform system, what I have is that the number of particles is three-dimensional too, okay? Is equal to, and then I have a sphere around me as I move away a distance r, right? But it's the same density everywhere outside of it. So as I go out, this r changes. Now, if I go in this direction, another particle is there, another particle, another particle, another particle, right? So it's just keep increasing with the distance that I take. And I'm putting a surface around it. In this case, is this red circle, but in 3 dimensions, it would be the surface of a sphere, right? So that surface would be given to me by 4 pi r squared, the size of that shell, and then this rho this is the density. It's a number, right? The density of the system. The density can be defined as rho is equal to the number of particles minus 1 enclosed in the volume. And then this dr will be the little shell that I put around it. So I have to put a circle in it, but it's not a finite, it's not an infinitesimal circle. It's more like a little shell, right? That's what my dr is. You can take it to that extreme when you're doing calculus, that it becomes an infinitesimal thing. But it's just the size of the shell, this dr. Questions? So this is the number of particles. Then we can ask, how many particles pairs of particles are separated by a distance r? So in this case, we can write it, and it would be 1/2 n times the 4 pi r squared dr times density. So this is because they're it's in a uniform system. That's why that's the case. They're all the same. It's the same in all directions, kind of like the most boring kind of system, right? Even the discreteness of it is not taken into account at this point because it's just boring, uniform, everything the same. All right, now, what if things get interesting and the particles are interacting? So the interacting, when a system is interacting, that's when things become interesting because new behavior comes out. Particles can crash with each other and change momentum with each other. When you turn on the interaction, the upper density volume is no longer uniform. All right, so let's do the math for the interacting, and it's gonna be similar to this portion right here, to this portion right here. So we're gonna take number of particles that is equal to the 4 pi r squared dr divided by the volume n minus 1. And this is the same as 4 pi r squared dr times the density. Now we have a system. We have this density here, we have the 4 pi, all of that. And this number of particles is going to be this density, some pair correlation function G of R, and the 4 pi r squared dr. In order for us to write what this pair correlation is, this is what calls interactions, right? If particles are not interacting, this pair correlation is just 1, and it doesn't matter. Like this. But because that's not uniform anymore, because the particles are interacting, we have to figure out what that is. And it's not 1 because the particles are not interacting. It's not going to be uniform because the density of the system is not uniform. If you have grains of sand, it's going to be different than if you have marbles that are 1 inch thick. So this correlation function is what tells you this is what the particles do. This is how they talk to each other. Make sense? We're good? So how does the correlation function work? The pair correlation function work. So let's try to figure out what this pair correlation should look like. So this G of R as a function of R. Looking at a system of interacting particles, right? If we have that the particles cannot be on top of each other, right? They're interacting and we're not allowing them to be on top of each other. They're not Bose condensates, right? What would be the value of GR when the distance is 0? How many pairs do you have that are on top of each other? 0, right? So it should be 0 here. This is region 1. So let's call about region 1. Two objects cannot occupy the same spot. So it should vanish at 0. That makes sense, right? what does this correlation function gonna do really far away distances? How many pairs can you make, right? As you go farther and farther away.
Will it also be zero?
Could you repeat your question?
Right, so how many? All right, let's take this picture right here. So this applies to this kind of system. They cannot be on top of each other, right? I pick a random distance. Let me pick a random distance from here, this point, the center of this guy to here. How many pairs are at that distance? Maybe two, maybe one, right? So you start picking distances r and figuring out how many pairs do I have. And as you go to very far away distances, you should always have one, right? There's at least one pair there. It doesn't matter the direction, it's just r, a distance away r. So over here, this is region 2. As r goes to infinity. Remember, we're asking how many pairs of particles are separated by a distance r. And you just start picking r's that are big. And there's always going to be a particle a distance r away from it, on average. Right? So now the question becomes, what happens here in the middle? Let me put an important length scale here. So we have the hardcore potential, right? Yeah.
So that does not mean that we have on average one pair, right? GR comes to one because at infinite distance, we will end up number of particles of rho pi r squared here, because at infinite distance, there is no correlation, there is no interaction in it. That's just our simple calculation we did in the previous.
Exactly.
That's GR is one, right? There will be like several thousands of pairs can be there at I would like this will be. Yep, but GR is one, is just taking care of the fact that the system will work like there is no interaction.
Yep. So is this one right here, right?
Yes.
Exactly.
That will fall into that.
Yep.
That's
All right. So then at this point, let's come up with the length scale here for our system. And we like this minimum in the potential minimum, right? Like, let's say we were dealing with the van der Waals or a Morse potential or something like that that has a minimum on it, like the ones that you're doing for the homework, right? So this is the potential minimum distance. We actually don't know what's the behavior in the middle until you start doing the calculations. So you can have something that goes and joins like this. Or you could have something that goes and joins and does this and then comes back down. And this is region 3. For 3, we do not know the behavior around this distance. You might have a peak. And what situation would allow for a peak?
When it forms a molecule. When it forms a molecule.
When it's attractive, right? So what did you guys have for breakfast? What did you have?
Maybe toast.
Toast.
Mhm.
Milk with what? All right, help me, Brian. What did you have for breakfast? No, I don't want to. You had Fruit Loops. Right? Luke, did you have?
A banana.
A banana. Nobody had Fruit Loops? Cheerios? Have you guys ever had Cheerios?
Cherry?
Cheerios, the cereal.
Cereal, yeah.
Cereal, yeah.
Never. Okay.
I,
You have?
yeah,
All right, Fruit Loops, Cheerios.
yeah.
Yeah.
Do the following experiment. Start counting how many. What is the structure of the form? You have 2 Cheerios, 2 Fruit Loops, and then they get close enough together, and then you're gonna see them kiss.
Like magnets do?
Exactly. Next time you have Cheerios, you do that. You guys never seen this. You never pay attention to your cereal.
No.
You guys really have cereal. You're like banana.
Bread and.
Avocado.
I'm more focused on crunchy cereal than watching it come together.
Crunchy cereal.
Yeah,
You.
you just let it sit and get soggy.
Alright, so
But is this related to like what happens to cereal? Is it not because of the tension of like?
yes, the tension
Adhesive force makes them come closer and fix each other, right?
and there's an attractive potential between them like that. And then they don't want to be on top of each other, so there's a repulsive portion of it. So your Cheerios come, see each other, and then they both
Yeah,
go into this meniscus in the water.
and tension satisfaction, then yes.
Yeah. So you might have that. If you guys ever decide to eat a normal cereal, less crunchy,
And it was just simulation that.
simulation of cereal right here. And they're gonna look like this, your Cheerios. You can start messing with the spoon like that and build the structures.
I do know that whenever, like I've seen, whenever there's like a few pieces of cereal left, they'll stick together because of the tension and just float around together. Does that have anything to do with that?
So that's what we're talking about. This is the attraction that they feel.
Okay.
If you have the Cheerios, Fruit Loops, you'll see it easier because they like each other like this. They're not gonna be on top of each other, but they're gonna be like this. So this region around it, right? The number of pairs that you see up, the pairs that get formed at this distance is higher than the volume around it. So that's the ratio that we're doing. How many pairs, like you said, how many pairs do we have, right? As you keep increasing this radius R and the volume keeps growing and growing. So your number of pairs grow, but the number of the volume that you're enclosing also grows. So that's where it averages to 1. In this case, we see that this volume that encloses here and the number of pairs is bigger than that volume on average. So you see that peak. So that's the peak due to attraction.
So wait, so the number of pairs, is it like pairs that are connected to like the central point that you're talking about?
Yeah.
Okay.
So if you were doing the simulation, let's say this was your simulation right here, you would see that there's that periodicity on it. And in this one, because it's periodic, it doesn't matter that they're close, that whether you do it on this one or the other one. So if it's periodic, it's going to be the same. When you're doing the calculation, you take an average over all of your system. So these little clusters that you're going to build next time you start eating cereal, they have this pair correlation around them because of that. There's more pairs around it. So therefore it's higher than just one particle. So that's what we're calculating here, right? So the only thing we know is that this G of R is proportional to the exponential of the potential that you had, that you're working with around this area. So when you have a fraction around this area, then you're going to see a peak. And it's just reflecting the potential's behavior. All right, so once you've done this, let me see if I can explain better what I'm talking about. At this point, I need to modify our definition of number of pairs. But this one right here, right? It's not going to be that one. Let me rewrite it. One half n times our G of R and rho, the density 4 pi r squared, and then the size of the shell that we're using. So what we want to do is calculate G of R, right? Yes.
Is this behavior just for gases or, I mean, you can see it in liquid also.
You can see it on everything. On all of the particles and all of the systems. Yeah. So
Regarding this.
the G of R, so just for those of you that are solid state physicists, sorry, high energy folks. If you do X-ray diffraction, what are you measuring?
The reflection of the
Sorry?
the peaks like descent, like higher.
Yeah, you measure things, right? And you're measuring the position. All right. So what you're doing is that you're measuring the scattering potential of the X-rays. So we call that one S of Q. Actually, this is high energy too, right?
Everything is happening.
High energy and low energy. Sorry. So when you're doing the scattering potential, you're measuring S of Q. S of Q. This thing is G of R. If you take the Fourier transform of your S of Q, you get G of R. Your X-ray diffraction pattern
Is reciprocal.
is the reciprocal of this correlation function. So if in the other one you had peaks at some points, when you do this G of R, you're also going to get the peaks. And those peaks form because you're in the X-ray scattering systems, you have the planes of perfect periodicity, right? Those peaks that we see in solid state when we're looking at X-ray diffraction also show up as dips and peaks in your correlation function. So it's the exact same thing.
What's the solid, I mean, that we can have particles on each other, not, I mean, they're just the beside, because we have a network of the organized, all the units. Is that,
So you cannot have particles on top of each other, right?
yeah, because, I mean, there is, I mean, then all there's network and they have repeated or not, I mean, a 3-dimension. This is the way I'm saying that.
So, well, basically particles, fermions, don't like being on top of each other. You cannot have two fermions on top of each other if they have the same quantum numbers. In classical mechanics, we don't want to put particles on top of each other because they don't like it. That's interaction potentials that we make. But you can make other types of interaction potentials, artificial interaction potentials that would allow them to be on top of each other. And maybe they have higher energy, but not infinite higher energy, like the hard boundaries that we put on objects. You could do that. So we want to calculate the correlation function, right? And figure out how to do it. And we do the following. This is my G of R. I will do the calculation. So this might sound challenging, but what we're basically doing is the following. We want to look at the number of pairs of particles within a distance R and R plus dr, and divide that by this number, 1/2 n times rho 4 pi r squared dr. So that's our definition. We have the number of pairs of particles, and then we have all of these quantities. We want to calculate G of R. So we just put GR on one side and take the rest of it down below. And we write it on here.
Dr. Will we be neglecting particles like apart from pairs? Like what if 3 or 4 particles are grouped together? So will we be neglecting those or?
No, you just count how many you have and then divide it by how many you expect to have. So this is kind of like you're expecting to have this many because of density, and this is what you actually have. And in principle, they average out to 1 at very long distances. So this is what you would expect from density, and this is what you're counting. I think it's just, I didn't explain it right at the beginning. I was trying to be more, trying to build it up. Yeah.
Back to your Curios example that you threw, you're defining a pair as, so in that example, it would be 5 pairs, because there would be there's 5 together. So that 5 pairs, where you count even the like.
So you go 1 pair, 2 pairs, 3 pairs, 4 pairs, 5 pairs. And there's 5 pairs around it. Yeah.
On the edges.
Because I will take a circle, right? So let's see. I have like, let's say that this is just random like that, right? And then I have another particle right here. What I want to do then is take a shell. This is my shell that is going to go around in a circle here. This is R. And then another extra shell right here that goes around it like this. And this is R plus dr. So now if we zoom in, right? I start counting how many I have. And I have inside my shell, 1, 2. And then I move my shell again and again and again and again and again, and I just keep counting. So that's what we're doing. And now we want to do that with a code.
How we could count them? Is it, I mean, experimentally or?
Experimentally, you would take a picture, like an SEM
Uh-huh.
or TM, and then you can get a program, you write a program to look for those dots, or you can just count them by hand. So computationally, you would make the following, yeah,
We are taking half of n level. So this half we are taking because
because they're half of n is the total number, half is the number of pairs, right?
is that we're doing that, or when we are taking the shell, we are just going through the radius of that molecule, right? So half of this molecule is there and half will be in the next section of this radius.
Yeah,
right?
yeah.
And we're taking all the molecules that is on the shell, that's the number of this molecule, and this number is exactly how many pairs they make with the, because everyone is making one pair with the center. So number of the molecule is equal to the number of the pairs that make with the center.
Exactly.
But half is because half of the molecule is in this shell. If we just extend our shell, other half will be in that case, right?
You can do that too, yeah, or you could change. I mean, this quantity right here, right?
Yes, like this n by 2,
Yeah,
because our molecule is just half part is inside the shell.
yeah.
Or is there anything else?
Well, it could also be that you have n molecules would be n particles. And you're looking at how many pairs you have, so you divide by 2. I actually don't know. I thought that that's why we were doing it this way.
But there's because this is the shell 4 pi r square.
Yeah,
dr, that's the shell.
Yep.
And we are multiplying it by number density. So that's the number
mhm,
that like that's their number density, right?
yeah.
So this n by 2, and so why is there half?
So my definition was here. We can ask how many particles are separated by a distance r, and this is pairs of particles. So that's why I put the half right here, right? So if you look, this is number of particles is equal to this one. And then how many pairs do we have would be half number of particles and that quantity. That's where I was getting the half, because you were making pairs. So if you wanted to make not pairs, but 3 or quads or penta of those, you would divide by 3 or 4 or 5. That's what I think, but I'm not completely sure. All right, so this is the way to build a computer code, right? You divide R into bins. So each location is going to be a bin. So we're going to have this location, this is 0. And then you're going to put bins right here, like that. So this would be dr, 2 drs, 3 drs, 4 drs, 5 drs, and so forth. And then the bins are divided, and then you collect particles into each of the entries on an array. So for instance, if you're looking at the n bin, it would be like B of n. And you're putting this many, and this is the number of particles that fit in that bin. So this B of n is equal as the number of pairs in that bin. Then you compute all distances between particles, right? You calculate this Rij. This set is gonna be something like 1/2 n minus 1 entries. So if you have 10 particles, right? How many pairs do you have? It's 10 times 9 divided by 2.
Oh, so that part, like there, it's actually NC2. Like we have 10 particles in their shell.
Mhm.
We are making the pairs, so if it's
Exactly.
10 particle, if we take 2 by those, so its NC2 is half into n into n minus 1. And since n is large, so n into n minus 1 is n,
Yeah.
just n in it. That's
the 1/2,
that's how
exactly.
it comes from.
So you do this. And then you start looking at how many on this set fit on this bin, then this bin, then this bin, this bin, this bin, and so forth. And you start building them, and you're adding guys to your bin. And you're basically getting a quantized version of this plot right here. So you would know that here in the first bin is probably 0. Maybe the second one is also 0. Maybe the third one is when you start seeing like maybe 1 particle and so forth. And then you will start filling little boxes here all the way up and so forth. Does that make sense?
Thermodynamic distribution.
All right, so when I stop right here, you're gonna be doing this, not in this homework that you're assigned, but in a follow-up homework. And then in the next class, I'll talk about why this is important, why we want to calculate this GO bar, although I have given you some hints, right? Like for instance, it tells you about the structure of the system, because if you have a crystal system, you have a unique GO bar.
Question, does homework do any relation to the last session?
Sorry?
In your question, does the homework do has any relation to the last session or?
Maybe, but the notes are in the website. Yeah.